In this video, I will go over the basics of understanding images, vectors, matrices, and then finishing with the idea of a manifold. So, a medical imaging scanner can be regarded as a system that is imaging some function in the field of view. Now, that function in the field of view of the scanner, that's an object. So, for example, if we're dealing with PET imaging here, what we have is this system, which is a medical imaging scanner. And what we're doing is looking at an object, a continuous distribution. For example, the brain inside the field of view is a continuous distribution in terms of being a function. And typically, this is measured in some way. So with PET imaging, it's measured through detection of photons. This system then, the scanner, detects radiation from that object and delivers some output measured data. So the key of this slide is to understand that an object is in the field of view is regarded as a function, a continuous function, and when it goes through the imaging system, the output is another function, typically a discrete function, and we'll go into that in more detail. So that's what I'm summarizing at the bottom here. The object is often a continuous 3D or 4D. The reason I say 4D there is to account for the fact that this could change with time. If it's a 3D object, it could change with time. This is just a 2D continuous function, if you like, a slice through the patient's brain. But in general, it's going to be a 3D distribution that can change with time, and so that's a 4D function. And this system, the medical imaging device, is effectively an operator or a mapping taking us from that continuous function to a discrete function. So that's a very basic overview of input through a system to deliver an output, which is measured data. So now it's really important to understand that object that is inside the scanner's field of view. Typically, in this example here, it's going to be something like a patient's brain. And here I'm just going to consider a two-dimensional cross-section through that brain. So this then is going to be regarded as a continuous function. So that's a value f depending on a spatial coordinate bold vector r. So that could be just x comma y to access x positions and y positions as continuous variables, allowing us to access with infinite precision any location inside that field of view. And then to have some value f, which in the case of PET imaging would be radioactive concentration, or if it's X-ray, it's going to be the related to the attenuation coefficient of the object. So this continuous object then, often when we're dealing with image reconstruction from the measured data, we're never going to be able to recover that continuous function description. And so what we're going to do is represent that continuous object in a discrete way, such as what I'm showing here, whereby we use small pixel basis functions or voxels in 3D, pixels in 2D. And so we're saying that continuous function here, f of r, is therefore a summation of these discrete pixels, b as a function of r, each with a particular scale factor, amplitude, or coefficient, whatever you want to refer to it as. And so here I've exaggerated the discretization of this continuous function, first of all with a 50 by 50 pixel grid, and then with crudely an 8 by 8 pixel grid. The point being that we are now representing that continuous function with a very small number of parameters. So here in the 8 by 8 example, it's going to be 64 values, which we could stack into a tall column vector, which I'll call theta. And so that's telling us the amount, theta 1, of basis function B1 located in this position in the field of view of the PET scanner. And so just to clarify that even more, here I'm just explicitly labeling theta as, if you like, the coefficients or the parameters that are going to represent that object, okay? So really, image reconstruction, because what we're showing on this slide is what image reconstruction is all about, which is how do we recover this unknown object. Image reconstruction is all about estimation of parameters or coefficients of basis functions, but in general parameters that represent that object. Again, we cannot recover, we're never going to have an imaging device that can capture all the information, so we're always only going to be estimating a representation of the object inside the field of view. Right, so here I'm going to go through to make this a bit more explicit by considering just 3 of these pixel basis functions in this discrete example. And here I'm showing a common choice of the pixel, which is the rectangle or the top hat function. So in 1D that would be like a top hat profile, but in 2D it's like one of these squares, but we'll see it represented in the next slide. But just to show, therefore, that this continuous function f of r is represented by a summation of pixel basis functions, 2D rectangle functions, and I'm showing here that we could use exactly the same rectangle basis function, rect of r, just shifted to the location of pixel 1. So this would be pixel 1. So if you like, here the summation is j equals 1 to capital J pixels. So that would go up to 64 pixels here. And for each one of them, we're just going to take that basis function as the rectangle function and just shift it to the center position. So let's look at the second pixel basis function. So that would be, in general, could be any spatial basis function. So here it's just b2 of r, and I'm saying, well, okay, let's keep the same spatial basis as the rectangle, the 2D rect function, and just shift it now to the center of pixel 2 in this xy space. And likewise for the third pixel value, again it's just the 2D rect function shifted to the center of that pixel. And so we could carry on like that to cover all 64 pixels as a discrete representation of that continuous 2D function, which is what we're trying to supposedly reconstruct. Again, image reconstruction should be relabeled as estimation of object representation parameters if we're being strict. So here then is a clearer depiction again where this heavily discrete example of 8 by 8 pixels, I'm now showing them as rect functions, these 2D pixels, and you can see that the height of these 2D pixels shown on this axis here is actually corresponding to that coefficient or amplitude or scale factor theta j, where that theta j is the scale factor or coefficient for pixel basis function b subscript j. So the 3 examples we just saw, where we just looked at the first 3 pixels, the yellow numbers there just correspond to the coefficients, and you can see that that would be those 3 there, which are of 0 amplitude. As we go towards the middle here, we get values of 100, and so you can see that corresponds to those pixel basis functions. In the less extreme discrete case shown here, you can now see these little tiny pixel basis functions, and again I'm just representing the grayscale value as a height now on a visualization of a 2D function. But of course in reconstruction we don't really represent images in this way here, represent objects. We typically show them as grayscale values as a function of x and y position. So I hope this slide is clear. The take-home message is that with image reconstruction, really we're trying to estimate this continuous function f of r inside a scanner field of view, and we can only ever do it with this rather simple discretization which reduces the parameterization. Because you could imagine, just to go one step further with this, the missing kind of picture here would be, if you like, Dirac delta functions, in other words, kind of infinitely kind of narrow, infinitesimally narrow pixels, whereby we would actually need an infinite number of coefficients to represent this continuous function. But in general, what we're doing is reducing the dimensionality of the problem to just a limited number of values theta j, which make up a tall column vector. Right, so with that in mind, I just really want to now do a very brief tutorial on better understanding of vectors and matrices. So as you've just seen in the previous slide, a vector is like a tall list of numbers, okay? So signals or images or functions, when discretized, can be regarded as vectors, just a list of numbers. So likewise, images can be regarded as vectors, signals can be regarded as vectors, and indeed matrices, which we're going to touch on in a moment, are just really very convenient to be understood as collections of vectors, either in rows or columns. And I'll touch on just some examples very briefly during this talk to go over some examples that are relevant for understanding matrices for the context of medical image reconstruction or image reconstruction in general. Right, so 1D functions as vectors. Here's a continuous function, so a value f, which is just changing according to this arbitrary function I'm showing here, changing in accordance with spatial independent variable x. A discrete function could be shown like this. There are many different ways of representing discrete functions, but I'm just showing an example here, a value f, now with square brackets to denote that I'm only going to have discrete locations on that independent variable x. Now often people would use a different notation here. They wouldn't use x, they might use something like n to indicate it's an integer value or some discrete step size in this independent variable. But notice again, just like we saw before when we're dealing with the 2D image, we've got a continuous object if you like, but we're just doing a discrete function representation of that. And so here, if you like, we've got these kind of delta function basis vectors, and then we've just got little scaling coefficients for each one of them. Point being, we can represent this as a vector. So here I've just got a sequence of numbers just crudely represented here. I've put it in a row, and that's why I've got a transpose here to show that normally it would be a column of numbers, a vector. And so just showing that that function could be represented as this list of numbers. And we could often see this kind of notation here. A vector f is just an element in a j-dimensional, if we've got j values, capital J values here. So I haven't counted how many there are here, but in general we'd have 1 to j values in our vector f, and therefore the vector f sits in a j-dimensional vector space where each of the values in f, here I've just got integer values, but in general they're going to be real values, okay? So we're saying the vector f sits in some vector space where there are effectively j dimensions. And notice that very high dimensional vector space, because j could be typically millions, in fact, in size for image reconstruction. Notice that that could be used, for example, even to just represent a 1D function. Often we'll use it to represent a 2D, 3D, or 4D continuous function, the object inside the scanner field of view. Right, so now I've done the simple case of a 1D continuous function, or likewise a 2D continuous function, a bit like what you saw before, could also be represented as a vector, and this is kind of something you've already implicitly seen from before. I'm just now explicitly again showing the values inside here, an empty image. Here I've just used a kind of a white value to denote a value of 0, and so if we had a 5x5 grid as a discrete representation, that would just be 25 values, so it's just a tall column vector. Another very simple example image, we could have, say, a letter A here, and here if I just use white here to denote a value of 0 and red to denote a value of 1, then again this very crude 5x5 pixelated grid will just be a list of 25 numbers, which again is a vector. Okay, so we've seen 1D functions can be represented by vectors, and the dimensionality of the vector depends on how many samples you've got of the 1D function. Likewise, 2D images, depending on how many pixels you have, can also be represented as a vector of a certain number of dimensions. So here with 5x5, we can be explicit and say that an image is a 25-dimensional vector. Again, so therefore vector f sits in a 25-dimensional vector space. Now I maybe should also clarify here that earlier I was using theta as coefficients, and here, if you like, implicitly I'm using a bold vector f. Here you can change notation as long as we're clear on the definition of the vector, and so here I'm just using f rather than theta. Right, okay, so now on to matrices, and it's really important in signal and image processing and in image reconstruction. It's useful to regard matrices as collections of signals or images, in other words, vectors, like we've been talking about So therefore, you can see there, a matrix is effectively a grid of numbers. And all I've just shown there was that every row is just a list of numbers. And as we've seen, a list of numbers represents a signal, a function, an image, an object, whatever it is that we're seeking to represent. And so likewise, the columns of a matrix are also can be regarded, of course, as vectors, and therefore the columns can often be visualized as signals or indeed as images. So, general description of a matrix then, often I will use I equals 1 to capital I rows to talk about my kind of matrices of interest for medical imaging. And those, again, can be regarded as signals or images. And often I'll deal with 1 to capital J columns to represent, so capital J to represent the number of columns in my matrix, okay? So I'm labeling the columns as J equals 1 to capital J, okay? So row 1 to row I, column 1 to column capital J. And then, of course, sorry, what I've missed out here was saying that, of course, for each of the rows we just saw earlier, there were, of course, 1 to J elements in each row, and for each of the columns, which is what we're looking at here, the columns, there are, of course, 1 to capital I elements in each column, because each column, of course, has all the rows in it, and each row has all the columns in it. So that's what I was just saying with those two sentences, those two paragraphs at the top. So typical representation of matrices, we've got some matrix A, which is a set of a 2D grid of numbers, basically. So we've got capital I rows by capital J columns, and therefore we've got I by J real numbers making up the matrix A. And so also we could say the matrix A is just an element in an I by J dimensional vector space. So these are, again, just real numbers. So matrix vector multiplication, I want to convey this very clearly. It's very important to understand this for image reconstruction. Typically, we've got some kind of mapping like this, taking us from a vector X to a vector Y. And let's just get those vectors in place here. So there's vector X. These are just arbitrary numbers for the sake of the example here. Remember, they can represent signals or images. So therefore, we've got an output vector Y and an input vector X going through a system matrix A. So let's take a look at matrix vector multiplication. So first of all, I want to convey clearly a row-based understanding of matrix vector multiplication. And what that means is that this first scalar value here, so here 25, so the first output element in the output vector is given by taking this first row of the matrix A, so I'm just calling that a vector R, and we take it in dot product or scalar product or inner product with the input vector X. Okay, so therefore an output scalar value Y1 is basically a signal or an image, which is a vector, in scalar product, in dot product, with an input vector, which is a signal or an image or a function that's just been represented discretely. And so therefore the scalar product of two vectors y1 is equal to r dot x. We could also write that in more conventional subscript notation as shown here, where this output scalar y1 is just given by this value 0 times this value 3 plus value of 2 times value of 1 plus value of 3 times value of 5 and so on. I'm just spelling that out here for the case of j columns, in other words j elements in a given row. So in row 1 there are j elements, capital J elements. So more generally then, going away from this vector r to now say, in fact, r is just a row of matrix A, therefore we can say output element 1 of the vector y is given by row 1 of the matrix A, and we just consider all of the elements j equals 1 to capital J in that row of the matrix, multiplied point by point by point with all of the elements in input vector xj. So j is now accessing here, of course, the rows of that input vector x. So once we've done the product, we sum them all up and that gives us the scalar output. Now in a moment I'm going to link this to real-world imaging examples, which is really important for understanding in image reconstruction. So there you go, I've just finished here with the generic case of element I of output vector y, which is that whole vector on the left-hand side there, is going to be in general a signal or an image or a function representation dot product with an input function signal or image. Okay, and so that's why we have this notation here, which we will revisit again towards the end. Right, let's begin to build up to the practical imaging example then. So let's understand what is happening with the row, the scalar product matrix vector multiplication I've just been talking about. In other words, row in dot product with an input vector. So this is an input vector x. So relating that to the earlier material, that could be regarded as, these could be regarded as coefficients for some pixel basis functions for an image, for example. But here we're keeping it compact, so just 5 values. So this is our signal or image, okay, represented by 5 values. Then we're going to be multiplying that point by point by point with a row of that system matrix A. So here I'm showing a row I, and I'm just picking out 5 values. There are 5 columns assumed here in this matrix A, corresponding to 5 input values in the input vector X. Now here I'm using square brackets K, because we're going to be summing over that. I could have used subscript K, but here I'm just kind of showing it's effectively a discrete function. So I'm mixing notation here because I'm also using subscript I to denote row I. But don't worry, I'm going to tie this all together in the maths at the end here. Right, so matrix vector multiplication using scalar products. What we've got then is an input vector x multiplied scalar product with a row of the matrix A. And so what that corresponds to doing is taking, if you like, the pixel value here of 4, multiplying it by, in quotes, the pixel value, so to speak, of the, in quotes, image or whatever the visualization is of a row of the system matrix. I'll show you a concrete example in a moment. So we take that pixel value, multiply it by that pixel value to get the output pixel value. Do it for the second one, so 5 times 0 is 0, 3 times 2 is 6, 2 times 2 is 4, and so on. So this is just a point-by-point multiplication of one set of points with another set of points. And then, to finish off the scalar product, we need to sum them all together to get some output value, which here is just going to simply be a value of 14. So that's why it's a scalar product. Okay, so with this mix of notation here, I'm saying a general output element of vector y is just the input vector multiplied point by point with a row of matrix A, sum it all up over all of the values, and that gives you that scalar output. Right, let's move on after I've just shown the more conventional subscript notation here. So I'm saying output element yi is given by row I of the matrix A. Consider all the columns in that row, multiply them point by all the elements in vector X, sum them all up, gives you the output. Right, now this is the concrete example now. We're moving towards an example of interest, for example, in PET imaging or in X-ray CT, where we would have the object now represented as a vector x. Again, notice how many different forms of notation I'm using here. It could be theta, could be f, could be x. You've got to be very open to various notations here, okay? So we've got some input vector x, which is a signal or an image. Here I'm showing it as a discrete 2D function. And what we're going to do is do a line integral, because that's part of the discrete radon transform, which is integral, which is part of, for example, X-ray CT, or indeed even part of PET imaging forward models, which are going to be needed when we get to reconstruction. So what then we're doing with a line integral, to achieve a line integral by matrix vector multiplication, what we need then is the input image x, and then for the matrix, one single row I of matrix A is actually going to be, if you like, a picture of the line that we want to integrate along. So all we've got to do for any given line integral, so if taking this line integral, this is a 2D discrete representation of that image, if you like, of a line. And again, for scalar product, all we do is take each of the values, so we just scan across all the values in that input vector x. Here you can see I've got it in a very high dimensional form. This is very high sampling, maybe 256 by 256, so a very high dimensional vector x. We just visit each pixel value, multiply it by each pixel value here to get this product image here. And so you'll notice wherever we've got values of 0 in x, or wherever we've got values of 0 here, we would get values of 0 in this output. Now, okay, for clarity here, what I've done is I've still shown where that brain object is, but really when you take this multiplied by this, all you're going to get is that line there that intersects that brain. The rest of this would be 0. Okay, and then to finish the scalar product, what do? We sum up all the values in that vector. This again is just a high dimensional vector. Sum up all the values. And what that's going to be doing then, remember it's only going to be non-zero along that intersection line there. When we sum it all up, it's effectively taking the sum of all the values just along that line through the brain, and so therefore it has achieved a line integral. Okay, so all the same notation as the previous slide carries through here, and again I'd really point you to the notation really on the bottom left corner here. So the output of our line integral y, okay, for line I is just given by, if you like, the signal, the picture of the line that's doing the line integral, just multiply point by the input vector, sum it all up to give a line integral. This then is at the core of a discrete radon transform used in PET imaging, for example, or used in CT. Right, MR, often you're dealing with K-space or measuring, or rather what we're going to be doing is modeling K-space for a given image when we're doing reconstruction from K-space data. And so that means we need to model what a Fourier transform is doing. So it's exactly the same mechanism. So if we've now got this same input vector x, but now we want to find the value. Here I'm just dealing with real values, but of course this could be a complex matrix A, it could be a discrete Fourier transform. But just to give an example here of just a real component of the Fourier transform, what we need to do then to get this value, this real part of K-space here, all we need to do is just take the input vector x, multiply it point by point by the particular 2D spatial frequency that we want to find in K-space. In other words, what is the amplitude of this two-dimensional spatial frequency component, which is part of making up that image. Because of course this image is composed of all of the various 2D spatial frequencies with various coefficients, and that makes up that image here. But anyway, a forward model for MR imaging is going to be a discrete Fourier transform, and we could represent a discrete Fourier transform in this way just by considering all the different rows of a matrix A, where all the different rows would all be all the 2D spatial frequencies. And I'm just showing here an example of one spatial frequency represented by these kind of, this is going to be positive, negative, positive, negative, a sinusoidally varying function. And to perform the discrete Fourier transform, all we do then is, again, the same process. We just scan across here, pixel value by pixel value, multiply it pixel value by pixel value with the particular sinusoid that we want to use to get the discrete Fourier transform for that particular sinusoid, for that particular spatial frequency. Once we've done the product, we get something like this. Again, I've just represented this where you can still see where the brain was. And in fact, of course, you would still see all the different particular outline of the brain here because this is positive then negative in this sinusoidal function. And once you've done that product, so this is, if you like, image times sinusoid gives us this. Once you've done that, you sum it all up, and that's going to give you something that is proportional to, not directly equal to, because often there are normalization factors in here, proportional to the Fourier coefficient for that spatial frequency that is present in that image x. Okay, and so the same notation applies. Again, would prefer that you focus on the bottom left notation there. Right, so that's, I hope, cemented a bit of understanding row times input vector, scalar product, row-based understanding of matrix vector multiplication. So I also now want to touch on column-based understanding. Again, remember the columns of any matrix can be regarded as signals, images, discrete functions. And so here I'm showing what happens when we consider a column-based understanding of matrix vector multiplication. So we've got input vector x here. So these are values 3, 1, 5, just arbitrary example values. And what I'm showing here is I'm just taking each of those values in the input vector x. Remember, there are as many values here as there are columns in the matrix A. That has to be the case for the matrix vector multiplication to be valid. Remember, we need that number to match that number in terms of number of elements. Okay, so all we're doing is taking these values and placing them, this is just for illustration, placing them as weighting factors on each of the columns. And once we've placed the weighting value of 3 on this signal or image, weighting value of 1 on that signal or image, and so on, once we've done that, okay, so that's what I'm showing there, weighting factors regarding that input vector x as weighting values. Once we've weighted all of those column vectors, we then sum them all together to get the overall output. So that's what I'm showing, I hope, with this illustration. There you go. So all of those columns were weighted by the input values, each element of the vector x, weighted and then just simply summed together. So therefore the output vector is a weighted sum of, if you like, signals, images, discrete functions. Okay, so that's the output vector y. And here I'm just showing that in various notations. So we could consider xj as an arbitrary element in that input vector x. And that's a coefficient or a scaling factor, a weighting factor for column j in this matrix. Sum them all up and that gets you the whole of the vector output y. So remember with the row-based understanding, we were doing scalar products, we were getting output values one by one by one. Here now we're getting the entire output vector y. And so we could show it in that notation, but again I'd really prefer that you focus on the example I gave earlier in the bottom left corner of the previous slides. Okay, so notation then, in fact this will now just actually show you the notation I do prefer, which was on the bottom left corner of those earlier slides, where we've got basically a vector y is equal to matrix A times vector x. In subscript notation we'll be using this. So again, all that I've just described in the previous slides should now, I hope, help you to understand this. You can do a little sanity check here, which is to make sure you've got your subscripts labeled correctly. We're summing over this index j, which appears here and here, and given that we're summing over that index, therefore that index j does not appear on the left-hand side. Okay? It's just like if you integrate with conventional continuous integration, integrate out a variable, it won't appear on the left-hand side output expression. And likewise, the index that we don't sum over, so here I, we're not summing over I, therefore that index I appears on that left-hand side. Right, I'm just going to wrap up now by talking about manifolds and then we're done. Vectors are all you need, really. That's what I'm trying to get at. For any continuous function that you can discretely represent, you can always capture it with a vector. So here then is a continuous function f of xy. There's the discrete function f square brackets xy to show it's a discrete integer values of x and y now. And there's that discrete example from earlier, 8 by 8. And remember the 8 by 8 pixel example, we just need 64 values, the grayscale values for each of those pixel basis functions. Now, I want to now convey this in the context of manifolds and high-dimensional vector spaces. So here we've got that's the continuous function representation. Here we've got 50 by 50, here we've got 8 by 8. Now let's go one step further and just consider 2 pixels, okay? So I'm just going to consider a pixel value of 75 here and pixel value of 20. So that's just a 2 by 1 column vector back to theta now. So of course, That's just, if you like, a coordinate. A vector, is pointing to a coordinate in a vector space. So here we can define a 2D coordinate system, orthogonal axes here, θ1, θ2. So we go a distance of 75 along θ1, view that as the x-axis if you like. Then we go a distance 20 along the second axis, θ2. And that means that those two pixel values correspond to a point in a two-dimensional space. Okay, so if we were now to consider any and every combination of pixel value pairs, then as we move around, basically any pair of pixel values would correspond to different locations in this two-dimensional vector space. Right, now let's go back and now say, well, what if we considered 3 pixel values? Okay, so if we just now had 75, 20 and a third pixel 25, notice we've got to be consistent ourselves with how we position these basis functions, and I refer you back to the very beginning of the talk where we had spatial basis functions. The spatial basis functions are the ones that are key for defining the dimensionality of the actual function we're representing. Here, remember, with these vector spaces, we're talking about the coefficients for basis functions that are positioned according to our definitions. So here now we've got 3 basis functions positioned in these three locations, and we've got coefficients or amplitudes 75, 20 and 25, so I've just stacked those in a 3x1 column vector. And of course, if we've got a vector of 3 elements, that's none other than a point in a 3-dimensional vector space. Okay, so we just have the θ1 axis, θ2 axis, θ3 axis, just take a real number along those axes, and therefore all the possible values of a 3-pixel image just correspond to all the possible locations in a 3D vector space. So now moving back towards the more practical example, if we now have a discretization that's a 50 by 50 pixel image, 50 by 50, that's 2,500 values, which would be stacked in a very tall column vector theta. Now my illustration breaks down here. It's very hard to show a 2,500 orthogonal axes, but that's somehow what you've got to get in your mind, that you've got 2,500 independent orthogonal axes here. Then this image here, this representation of an object, is just a point in a 2,500 dimensional vector space. So moving on to very highly sampled images. Now here I'm departing from medical imaging just to include a natural image, a photograph here in grayscale. So here we've got a 10 megapixel 2D image, and of course because we've got 10 million pixels here, 10 million spatial basis functions, therefore we've got 10 million coefficients, and so those coefficients are just this extremely tall column vector theta. Therefore this photograph would be a point in a 10 million dimensional vector space. Okay, so the point is, of course, we could consider any and every photograph. Okay, so any and every photograph would be a point in this 10 million dimensional vector space. And what I'm showing here is the notion, I'm only using this notation loosely, but many of us in the field do speak in this way, so please accept the rather casual definitions here because it's what's commonly done in the field. What we can do here is have this idea of a manifold, okay? So what we could do here in this manifold is consider, if you like, parts of this high-dimensional vector space. Remember, it's a 10 million dimensional vector space. So we consider parts of it, then, and often in a continuous fashion, with a kind of a continuous sort of, if you like, a kind of a hyper surface, if you like. Then we could consider this as, for example, containing every photo of a river. So here's the River Thames. And of course, the photos of rivers can never be anywhere in that high-dimensional vector space. They've got to be in just part of it, okay? And so this manifold is capturing, indicating the part of that high-dimensional vector space that captures all the photographs of rivers. And in fact, it gets quite philosophically interesting because, of course, these high-dimensional vector spaces are really quite mind-blowing, really, in their immensity, because this manifold, if you like, would be so large because it has to consider every conceivable photo that ever has been taken and that ever will be taken of any river, anywhere, at any time. Of course, if that's the manifold we choose, the manifold of photographs of rivers, then of course that would define this. If we insisted that, okay, it's only for the River Thames, then of course that would be a smaller manifold, and so on. Now, this is a useful concept because when we get to medical imaging, maybe on the next slide here, for example, MR images, 2D MR images, are occupying another manifold of that high-dimensional vector space. PET images, another manifold, and so on. So hopefully that's a useful concept. And in fact, this will come in very handy when we get into understanding deep learning for medical image reconstruction. Okay, I'm almost done on this lecture here now, just to say that if we press it even further to really the ultimate fine sampling, and in fact back to the continuous function representation, in fact it's no longer a representation, it is the function, then a continuous 2D function, in other words where the sampling is now infinitesimal and dealing with Dirac delta functions, continuous Dirac delta functions, then a continuous function can be regarded as a point in an infinite dimensional vector space, because we'd have infinitely many samples that go along x and y to capture that continuous function. So now, if you like, this would be an infinite dimensional vector theta, and that's where we get this kind of representation here from, where we're now dealing with, if you like, the grayscale value here being the coefficient for a Dirac delta function, each one of them shifted to every conceivable location in that in the independent variable xy, here denoted by a vector r. And to help understand that, again, I just point you back to where we started, to say that a continuous function is approximated by a summation of pixel basis functions with coefficients theta j. So in this continuous description here, the coefficients are in fact just the function value itself, if you like, scaling a basis function, here the delta function, whereas here we've got a general pixel, doesn't have to be a pixel, some kind of 2D spatial basis function. So therefore I'm just showing the link between the continuous description and a discrete description, and it's of course the discrete description that we'll have to work with, because we cannot go about estimating infinitely many parameters when we reconstruct an image. We're going to have to do a discrete, reduced dimensional description of our object. So I hope you found this useful. Thanks for listening.